Dear students, now we are in the last class today, and this is your Clausius-Musoti equation. And to derive this Clausius-Musoti equation, we require the bit concept of your Gauss law of the electrostatics that we have already done. So let us look into. So now first let us see the relation between the vector E is the electric field, D the your displacement current or the electric flux, whatever you say, and P is the dielectric polarization. So what is the relation between these three vectors? These three vector relation between these three vectors is required to find out the Clausius-Musoti equation. So now here let us suppose here we have your parallel plate capacitor. Here we have kept a parallel plate capacitor, as you can see over here is a parallel plate capacitor. So capacitor has been applied with a certain potential. So let us suppose potential that has been applied is your V is the potential that has been applied, and under that potential, so naturally this plate is getting charged, and therefore we'll have the electric field between this, and this direction of the electric field is from positive to negative charge, and this is the value of your electric field. Now between these two dielectric plates or parallel plate capacitor, we have placed a dielectric material. So here you see here in the figure number 2. So here I have placed a dielectric material. So naturally the dielectric material is again, see, it may be solids, liquid or gas, whatever it is, but it is made of the atoms, and therefore its atom is getting polarized, right? That is your electron cloud, and the nucleus is getting shifted, and that is going to generate your dipole. And because of that, what we are finding here now, you are, as you are getting here, you are getting the charge is getting separated. So this is the separation of the charge. Now what will be happening over here is, due to this plate we'll have the value of the electric field from positive to negative direction. So this will be the value of your electric field, because this is your positive plate, this is your negative, this is your positive plate as you can see over here, and this is your negative plate as you can see over here. And due to this plate that I have inserted over here, again there will be electric field from your positive to negative. So this is the direction in which you will have your electric field within the plate, right? So now naturally these two electric field are in the two different direction, and therefore the resultant electric field will equal to your E minus E dash, or whatever the nomenclature we can give it. And this can be solved by using the Gauss law of electrostatics. So from Gauss law of electrostatics, what we know, the line integral of the electric field, or E dot integral of E dot ds equal to Q upon epsilon naught, right? So line integral of the electric field E dot ds is equal to Q upon epsilon naught. Epsilon naught has been left over here only, and this is your Gauss law of electrostatics. So this I am going to apply on your first figure number 1, right? And where E is your electric field, Q is the charge that we have given, and of course across this we have drawn the Gaussian surface. So if I'm going to integrate this, so what I'm getting here, the E dot ds is there. So the integration of this will be your area. E will be coming out of this integral, and therefore we are getting the area, and the value of E is equal to your how much? E naught. E naught is the electric field that we have is being generated, right? So E naught into A equal to Q upon epsilon naught. So in this way we have calculated what is the value of your E naught. So E naught equal to Q upon A epsilon naught. Now let us see in the second figure. So again in the second figure, same concept we have applied. So line integral of the electric field is equal to Q upon epsilon naught. But now here you see you have the two type of the charge. One, the charge is due to the plates. That charge you have taken Q, and this is inside of this, and this charge we have taken as Q dash. Let us suppose this charge that has been developed over here, that has been taken as Q dash, right? So naturally the effect that we are getting is line integral of, since these two are in the opposite direction, as you can see the electric field that has been generated are in the two different directions. So what we can say, line integral of the electric field that has been generated is equal to Q minus Q dash, right? So again we have integrated this. So integral of this will equal to your A, so equal to epsilon naught has come on the right hand side. So Q upon epsilon naught minus Q dash upon epsilon naught. So the value of the E, the electric field inside your plates with your dielectric, you are getting is equal to Q upon A epsilon naught minus Q upon A epsilon, Q dash upon A epsilon naught. So without your dielectric material, the electric field that you are getting is E naught, and with your dielectric material, the electric field that you are getting is a E, and E is equal to how much? Q upon A epsilon naught minus Q dash upon A epsilon naught. All right. Now Q dash upon A is within this plate, right? So this is your, here you are getting the Q dash upon A, right? And because of this you are getting the polarization. The atoms are getting polarized, and therefore this can be given as the polarization. Q dash upon A can be given as polarization. So this is the what I'm writing in this equation. Let us suppose if I'm getting this equation as 1. So this is what the value I'm going to substitute. So Q dash upon A is equal to E. Now, so value of E I'm writing, right? And the value of Q upon A epsilon naught I am going to calculate. Q upon A epsilon naught. So just I have rearranged. Q upon A epsilon naught is equal to E, right? And this value I am writing Q dash upon A. Q dash upon A is equal to P. So this Q dash upon A is equal to P, right? This value have been substituted over here. So P upon epsilon naught. So what I am saying, Q upon A is equal to epsilon naught into E plus P. So what I have taken, epsilon naught has been taken on the right hand side. So this epsilon here, the epsilon is getting multiplied, and here this epsilon naught will be getting cancelled. So Q upon A is equal to epsilon naught into E plus P. Now D is known as your Q upon A is nothing, this your D, or which you can say your flux density, or you can say the displacement vector. So D is equal to, so now Q by A I am substituting as D. So D equal to epsilon naught here, epsilon naught into E plus P. So this is the relation that we will have to remember, that D is equal to epsilon naught into E plus P, where P is the polarization within the plates. So what we can say, E is the electric field that has been applied over here. So this is the electric field between the plates, right? The net electric field we can say, which is the difference of these two, right? And D is the flux density or the displacement vector, whatever you say, and the P is the polarization. So this let us suppose this is your equation number 2, and this equation is very, very important, and this equation I am going to apply in the Clausius-Musoti equation. So now let us look into how we can apply this equation to derive the Clausius-Musoti equation. Clausius-Musoti equation is being used for the single type of the atom, where we have just one type of the atom is there, and if we have to find out the dielectric constant in those type of the material, then the Clausius-Musoti equation is applied. So now let us derive the mathematical equation for Clausius-Musoti equation. So dear student, we have already seen the relation between the vector P, the flux density D, and the electric field E. We'll have to use this to calculate the, or to derive the Clausius-Musoti equation. Now I have already told you the Clausius-Musoti equation is applicable in the elements which have the one type of the element. That is, some elements, solids like the germanium, silicon, diamond, sulfur, etc. are made of the single type of the atom. These solids give only the electronic polarization. Thus, the total polarization of these solids can be given as P is equal to N alpha E into E dash, where E dash is your total electric field. Total electric field includes the field that we have given from the outside and the field that has been internally generated because of the polarization, right? So this value we have already seen this relation between the electric field and the polarization and the dipole moments, right? Now let's substitute the value of the electric field that we have derived. So P is equal to N alpha E, and the value of the total electric field, that is your E dash, is equal to E plus P upon 3 epsilon naught, and this value we have already derived. That is, the value of the E dash is equal to, in the internal field yesterday, E plus P upon 3 epsilon naught, where E is the applied electric field, P is the polarization, upon 3 epsilon naught, right? So this value I have just substituted in the equation number 1, right? Now this value we have already derived. We have derived D equal to epsilon naught into E plus P, where D is your flux density or the displacement vector, E is your applied electric field, right, from the outside that you have applied, and P is known as your polarization, right? Therefore, what I am going to do is, all the terms in this equation has been divided by E. So what we can write? P upon E is equal to D upon E minus epsilon naught, right? So P upon E, just I have done a bit rearrangement, that is this has been brought this side, right, by dividing this. So this is the value that we are getting, right? From the definition of the electric displacement, that we know D is equal to epsilon into E. This is the value of your D that we have seen in the Gauss law of electrostatics also, right? So that value of the D, I'm going to substitute it over here. Here you have got the value of the D, and this value of the D I'm going to substitute it there. So by substituting, what I can get is P upon E is equal to now this value I have substituted over here, so I can say this is equal to epsilon minus epsilon naught. Now epsilon can be given as epsilon naught into epsilon r into epsilon naught, where epsilon r is your relative permittivity and epsilon naught is your in the air medium. So P upon E can be given as epsilon naught into epsilon r minus 1. So therefore the value of the P that can be given there is, we have just you take out here E, so P is equal to epsilon naught into E into epsilon r minus 1. Epsilon r is your relative permittivity, or this is also called your dielectric constant. So this is an important relation, and you should always remember for your numerical point of view also, we'll be using in the numerical problem. P is equal to epsilon naught E minus into epsilon r minus 1. Now whatever the value of the P I have obtained, this value I am going to substitute in the equation number 2, and let's substitute this value and calculate the value of epsilon r, right? So now let us see so what I can say, this is the value in the equation 2 that we have, and this is the value that in the equation 4 I have derived. So this value I am going to substitute it over there, that is the value of the P I am going to substitute it over here, right? This is what I have told you in the previous slide, and then let us see what we are getting. So what we are getting is, now the value of the P, as you can see, is equal to your epsilon naught E epsilon r minus 1. So value of the P I have substituted it over here, and the value of the P again I have substituted over here also. So both the place I have just substituted the value of P. Now as you can see over here, you have your electric field E, and here also you have the electric field E. So electric field E I am going to take common. So if I am going to take electric field E common, then here you will have the 1. This electric field will get cancelled, right? So this electric field, and here since you have taken this electric field E as common, right? So if you have taken the electric field common, then this value become your 1, right? And this value of the electric field and this value of the electric field will get cancelled. So this is what I am going to do. So what I can say is n alpha E, that is the value of this I am going to calculate. N alpha E, this value is equal to how much? Epsilon naught into epsilon r minus 1 upon 1 plus, because now this has become 1 plus epsilon naught epsilon r minus 1 into upon 3 epsilon naught. So n alpha is equal to epsilon naught into epsilon r minus 1 upon 1 plus epsilon naught into epsilon r minus 1 upon 3 epsilon naught, and this value also you should remember, right? You can directly use for solving the numerical problem. Just I am going to rearrange this, right? So n alpha is equal to, just I have taken the LCM over here. So this has been taken as the LCM. So by taking the LCM, this is what I have done, the bit of the rearrangement, right? So the rearrangement has been done, and now this 3 epsilon naught will go up, and therefore it will come in your numerator, and therefore if I'm bringing it back, it will be getting divided over here. So n alpha E upon 3 epsilon naught can be given as epsilon naught into epsilon r minus 1 upon 3 epsilon naught into epsilon r minus 1. And I will suggest you that you should always sit with the pen and pencil and try to do this simple algebraic solution, right? So that you will have the clarity in your mind, right? So now what we can do, just I'm going to again rearrange, and whatever is the common that has been cancelled. Now what you do, you just open this bracket. So 3 epsilon naught into epsilon r minus 1. This also you can write epsilon naught epsilon r minus 1, and whatever is the common thing, just you cancel it, and the final value that we'll be getting is n alpha E upon 3 epsilon naught is equal to epsilon r minus 1 into upon epsilon r plus 2, where epsilon r is your relative permittivity or the dielectric constant. So what I'm saying, n alpha E upon 3 epsilon naught is equal to epsilon r minus 1 upon epsilon r upon 2, and this is called your Clausius-Musoti equation, and this should be remember. And you should also remember that this is primarily used where you have the single type of the atom is there. There only we'll be using this equation to find out the dielectric constant. Now we are moving to another one, the dielectric constant. So now let us see. Now the above equation is known as the Clausius-Musoti equation, which is valid for the non-polar solids having the cubical structure. The measured value of the epsilon r for the three elements that we had discussed there is, for the diamond the value is 5.68, silicon is the 12, and germanium you will getting 16. So these are your values of the epsilon r if you are going to calculate from using the Clausius-Musoti equation. So now I am going to move the dielectric constant. Now we have the primarily three types of the dielectric constant, right? Or the three types of the dielectric material. One will be the solid types, another will be the liquid type, and third is your gaseous type. So all the three types of the dielectric materials are available. So these materials are your solid type, the liquid type, and finally it is the gaseous type. And all these three types will have the different applications, which I am going to show you in the next slide. So in case of the solid, we can have the elementary dielectrics like super mica, germanium, diamond, porcelain, glass. So these are your elementary type. Then we can have the non-polar ionic dielectrics, which include high density polyethylene, polysterenes, lithium fluoride, and so on and so forth, the cotton ore. And then we have the polar dielectric, which is a Rochelle salt and C6H5NO2 and so on. So these are some of your solid dielectrics, and I am coming to the application of the solid dielectric in the next slide. Then we have the liquid dielectric. Liquid dielectric is your mineral oil, the synthetic oil, and the miscellaneous type of the oil. Transformer oil, the capacitor oil, and the silicon liquid are the other type of your liquid type of your dielectric material. You must be knowing in the transformer to stop the electrical shock or to stop the flow of the charge, we use the transformer oil. All right, and next we have the gaseous type of the dielectric, which can be the air, nitrogen, sulfur hexafluoride, and hydrogen. So these are your gaseous type of your dielectric material. Now solid dielectrics first. So dielectric material are mostly the solids. Some of them are the mica, as I have shown you in the previous slide, glass, plastics. Solid dielectric materials are used in capacitors. So most of them are used in the capacitors. Some of them are the mica, ceramics, barium titanate, quartz crystal is used to prepare the ultrasonic transducers. So you should remember these are the application of your solid dielectric. Similarly, we have the gaseous dielectric. Dielectric gas can be used as an electric material. It can be used to prevent the rapidly quenching electric discharge, right? So whenever you are using the electric discharge, right, so the charge should not quench out, right? So to prevent the quenching of the charge, right, to the flow out of the charge, we use your gaseous dielectric. Dielectric gases like air, nitrogen, hydrogen, and sulfur hexafluoride are used in the electrical insulator in high voltage applications like air capacitors, transformers, circuit breakers, and switch gears. So these are some of the applications. Of course, all these are your insulator, and here in all these applications that you have seen is this gas is being used as a insulator. And then finally we have your liquid dielectrics. A liquid dielectric is in the insulating dielectric material in a liquid state, and they are used to prevent the quick electric discharge. So again, gas is also used for the quick electric discharge to prevent the quick electric discharge, and this is also used to prevent the quick electric discharge, particularly in the case of the transformer. Dielectric liquids are used as the electrical insulator in high voltage applications such as the transformer, capacitor, and high voltage cables and switch gears. So there also we use the liquid dielectrics. Dielectric liquid can be used to provide the electrical insulations, suppress the corona, not this corona which is going on, that is the COVID, and they are saying to serve as a coolant. So corona is, now if you have the high voltage electrical cables, like let us suppose 11,000 volt electrical cable is passing, then your air medium can become charged, right? So to prevent that charge, some of the liquid material is being spread or it is being attached over there, and to prevent that, the liquid that we are putting, that will prevent the against the ionization of the medium, and that is called the corona, right? So it suppresses the corona effect in the high voltage cables. Thank you very much. So dear student, finally we have finished the entire syllabus as per all the 5 modules. Even though the module 1 and module 2 had completed during our normal classes, but still I thought that you may require some help at any point of the time. So therefore the lecture is already available. Whenever you find time or you require the needs, you can go back and you can enjoy the lectures. Thank you very much.